Hello friends, I welcome all of you to my chemistry YouTube channel. Today our topic is factor affecting chemical shift delta. This is an important topic in H1 NMR spectroscopy. So let's start our discussion. Basically there are five factors which significantly influence the delta value. In the list first we have the electronegativity of atom or group. The second is anisotropic effect. The third is called solvent effect. The fourth is hydrogen bonding. And the next and the last is electron density. So these five factors importantly influence the delta value, and we'll discuss a step by step. So let's look at the first point, electronegativity of atom or a group. Let's consider the methyl fluoride, methyl chloride, methyl bromide and methyl iodide molecule. In these, fluorine, chlorine, bromine and iodine, these are electronegative atoms, and if you compare the electronegativity of these atoms, fluorine has the highest value of electronegativity, that is 4, and iodine has the lowest, that is 2.6. Interestingly, the chemical shift delta value in parts per million is highest for methyl fluoride, that is 4.5. For methyl chloride it is 3.5. For methyl bromide is 2.7, and for methyl iodide is 2.2. So you can see very clearly the chemical shift value is getting changed with changing in the electronegativity of halogen atom, and thus we can simply say that the chemical shift delta is directly proportional to the electronegativity of atom or group within the molecule. Now let's consider the electronegativity order of carbon in acetylene, in ethene and methane molecule. As you know that in case of acetylene the carbon is sp hybridized. In case of ethene the carbon is sp2 hybridized, and whereas in case of methane the carbon is sp3 hybridized. The electronegativity order of these carbon is as sp carbon as having the highest electronegativity order, second is sp2 carbon, and third is sp3 carbon. So on the basis of discussion just now we have seen, we can say that the acetylene molecule hydrogen may have the highest value of chemical shift, but in the reality the position is different. So if you now check out very clearly delta value for ethene proton is 5.2 ppm, and which is actually higher than delta value for acetylene. Proton present in the acetylene has delta value of 1.8, and in case of methane delta value is 0.3. So if you are comparing alkyne, alkene and alkane, please remember these values. Remember that the alkene always have highest delta value, followed by alkyne, and the last we have alkane. So we can say that in a case of alkene, alkyne and alkane, the chemical shift order will be always for sp2 carbon, then for sp carbon, and for sp3 carbon. And these important point can be very well explained by second effect that we'll discuss, and it is called as a anisotropic effect. For your knowledge, the anisotropic effect is nothing but the non-uniform distributions of any effect developed in a molecule known as anisotropic effect. So if your investigating the molecule which has pi electron density in it, and the moment we keep such kinds of molecule in the external magnetic field H0, there is a development, there is a circulation of pi electron and which generate the secondary magnetic field. So these newly developed secondary magnetic field has the two different region within the molecule. The one region is called as a diamagnetic region, and in diamagnetic region the direction of applied magnetic field is reverse, is actually oppose the direction of H0. And the second is called the paramagnetic region, and the paramagnetic region is always parallel with the H0. So the two regions develop within the same molecule if you are applying the external magnetic field, and this is because the presence of pi electron within the molecule. Let's try to understand this effect. So if you are discussing any effect and if you are applying the external magnetic force and the effect is uniform throughout the molecule and we have equal distribution, that is called as a isotropic effect. On the other hand, if the developed effect is not uniform and not equally distributed, that is termed as anisotropic effect. So now consider the ethene molecule, and this ethene molecule now we are trying to investigate by H1 NMR spectroscopy. You can see that the ethene molecule is oriented perpendicularly with respect to applied magnetic field. And the moment you on applied magnetic field, what happen? The pi electron generate the secondary magnetic field, and you can see that arrows and the circle, this is called as a newly developed secondary magnetic field. And if you observe very carefully, one thing you can notice, in this region the direction of arrow are exactly anti-parallel with respect to applied magnetic field, and this is known as the diamagnetic region. Whereas if you observe the second region in which the actually hydrogens are placed, here the direction of newly developed secondary magnetic field exactly parallel with respect to applied magnetic field, and this is known as the paramagnetic region. So that means that within the same molecule which has the pi electron density, the ones we place in external magnetic field, they develop the two different region, diamagnetic region in which the direction is opposed with H0, and the second region is called as the paramagnetic region. And remember always that if the hydrogens are present in the paramagnetic region, they will going to have always higher value of delta, and the hydrogen if present in the diamagnetic region, they will always going to have the lower value of delta. And because of this effect, remember that the hydrogen molecules are present in ethene has a higher value of delta than the alkyne molecule. So in a conclusion, now we can say that hydrogen at diamagnetic region less value of chemical shift in a comparison to the paramagnetic region. If hydrogens are at paramagnetic region, they are going to have comparatively more value of delta. Let's discuss the third factor, solvent effect. Now in this case the ROH is alcohol, and this is our sample, and CaCl3 is our solvent. So you can see that the alcohols and CaCl3 both are polar molecule. Oxygen in the alcohol carry partial negative charge, whereas hydrogen has the partial plus charge. In the case of CaCl3 is also polar molecule. Chlorine has the partial negative charge and carbon has partial positive charge, and because of that polar nature, what happened, the alcohols and CaCl3 now develop the secondary interaction in which the hydrogen of alcohol is now linked with the chlorine of ClCl3 via hydrogen bonding. Next, let's change the solvent. Now we are using dimethyl sulfoxide, that is a DMSO, and alcohol is a solvent, and basically both are polar nature. So here the hydrogens of alcohol now engage in the interaction with the oxygen of DMSO via strong hydrogen bonding. And why it's strong? Because the electronegativity of oxygen is higher than the chlorine, and hence the hydrogen and oxygen linkage is strong as compared to H and Cl linkage. So you can see this kinds of effect also significantly influence the delta value. ROH, if its linkage with the chlorine, has delta value of 5.0 ppm. On the other hand, the alcohol, if it linked with the oxygen of DMSO, has delta value of 5.1 ppm. So you can observe very clearly there is an exact difference of 0.1 ppm, and this is how the solvent plays and also can change the delta value of proton in the concerned sample. Fourth effect is called hydrogen bonding. Now let us consider that alcohol in the molecule is free and it is not engaged in any extra bonding. In such cases, remember the chemical shift delta of this hydrogen will be always lower because it is not engaged in any kind of extra bonding. Whereas if the same molecule is now engaged with the extra interaction via hydrogen bonding, this hydrogen will have always higher delta value, because if it engages in hydrogen bonding, there will be net less electron density at the hydrogen, and that is actually this effect get prominent when we have strong hydrogen bonding. So we can say that the chemical shift delta for a proton is proportional directly to the strength of hydrogen bonding. And the next and the last, we have the electron density. Let's consider the active hydrogen nucleus. Once it placed in external magnetic field, it develops the angular momentum and magnetic momentum. You can see very carefully the direction of angular momentum L and the magnetic moment mu. They are parallel to each other and both are vector quantity. So L and mu are parallel in case of active hydrogen nucleus. Now in place of active hydrogen nucleus, if you are discussing the case of electron, and in the applications of external magnetic field, they develop the secondary magnetic region. And here the point to be noted that the angular momentum L and the magnetic moment mu both are anti-parallel to each other. Please note this point. These are the very important aspects when you are discussing the active hydrogen nucleus and the electron. In case of active hydrogen nucleus, L and mu are parallel, whereas in case of electron, and L and mu are anti-parallel. That going to affect the chemical shift delta in a prominent manner, and we can discuss that. So consider we have the nucleus and does not have any electron density. So it's kind of naked nucleus. For time being, we can consider the proton. Now in the next case, if the active nucleus has the electron density which are moving around it, and if you again increase the electron density, what happen here? Actually we are increasing the electron density. But if you now investigate the chemical shift value, please note that with increasing electron density at the active hydrogen nucleus, the chemical shift delta value is actually getting decreases. This is a very important aspect, and the answer can be suggested in a simple way. If you having the more electron density at the active nucleus, and if you are studying these kinds of active nucleus by H1 NMR spectroscopy by using external magnetic field H0, what happen if you on the external magnetic field, some of the magnetic field is consumed by these electron which are revolving around the nucleus. So for example, let's say you are giving a 1.41 Tesla magnetic field to the active nucleus, and what we expect that all 1.41 Tesla magnetic field should be experienced by that nucleus, but in the real cases some of the magnetic field is used by the electron present around the nucleus, and therefore 1.41 Tesla magnetic field will not reach completely to the nucleus, and that is how the chemical shift value is decreases, because this is also affects the precessional frequency of the nucleus. So in a simple way you can remember that the chemical shift delta of proton is proportional to the 1 by of electron density. So these are the very important factor which can influence the chemical shift delta value. Thanks for watching. Signing off, Dr. Atul Nagpure.